Alright, look, here's the challenge. My son is really stupid. He spent the last 30 years in high school. The only class he has left to pass is Physics C. He got a 30, like something, I don't remember. Maybe it was like a 70. Yeah, 30 points off the last 9 weeks. So he has a 68 this 9 weeks. In order to pass the class, he needs to pass his next magnetism exam. So that's where you come in. You need to help teach him magnetism. And if he fails the next test, I'm coming for you. He's over there.
Coming up next, it's Super Nanny. Where other nannies fail, Nanny Joe comes through.
This must be where the family lives. Hey, Mr. Ogon, my name is Mr. Mark. I'm here to nanny your son.
Alright, I'll show you where he is. Alright, so he's just going to be right down these stairs over here. Now look at my code.
Alright. Danger and beware. What's up with this?
Don't worry about it.
Okay.
Down these stairs. Make sure you teach him well.
Whoa, wait, where do you go? It seems like the door is locked behind me. And this is by far one of the weirdest families I have seen. It seems like this is a basement for his son. A lot of storage area. So here's the basement. I hear a door creaking. This is pretty weird. Hello, anyone down here? Okay. We have some Bud Light down here. The father's probably an alcoholic, like most families. Hello? Looks like a body bag, multiple bodies inside. I should probably call the police once this is over. There's no windows. Looks like there's no living beings down here at all. Whoa. Okay, this is pretty creepy. Oh, there turns out to be a son down here. Hello? Hello? My name's Mr. Mark. I'm gonna be your nanny for physics. Alright, listen here, you f***ing bit. If you wanna pass physics, you'll learn the formulas. But first, here are the units. First, you got F, which is equal to force newtons. You have Q, which is charge in coulombs. You have V, which is velocity in meters per second. B is magnetic field in Teslas. Theta equals angle in degrees. I is current in ampere. You have mu sub aught, which is the permeability of free space, which is equal to 4 pi times 10 to the power negative 7th Tesla times meters over amperes. You have L, which is length in meters. R is distance between two surfaces. A is area in meters per meter squared. And you have the flux sign, which is magnetic flux in Webers. N is the number of coils. T is time in seconds. And EMF is, which stands for electromotive force in volts. Alright, now that you have the units, we have to go on to the f***ing formulas. Okay, so first formula we have is magnetic force in a charged particle, which is F is equal to QV cross B. They don't give you vectors, you can use F is equal to QVB sine theta. Next we have magnetic force on a current carrying wire. So force is equal to the integral of I respect to length cross B, or if they don't give you vectors, FB is equal to BIL sine theta. The magnetic force or magnetic field from a current carrying wire, so B is equal to mu sub ot I over 2 pi r. The magnetic flux is equal to the integral of B respect to area, or you can use magnetic flux is equal to NBA cosine theta. The electromotive force, also known as Faraday's law, which we will be going over, is EMF is equal to the derivative of the magnetic flux over with respect to time, which is equal to the surface integral of an electric field with respect to length. Gauss's law, which is equal to the magnetic flux, the net magnetic flux is equal to the surface integral of the magnetic field with respect to area, which is equal to 0. The electromotive force in a railgun, so you have E, which is equal to magnetic field times length times velocity, and charged particle in a magnetic field, and this applies to centripetal force or centripetal acceleration. So you have QVB, which is equal to mv squared over r. For a non-symmetrical magnetic field, also known as Biot-Savart's law, I probably said that wrong, you have the derivative of the magnetic field, which is equal to mu sub ot I, dl cross r over 4 pi r cubed. And the magnetic field in a solenoid is, you have B is equal to mu sub ot and I, and magnetic field for a symmetrical object, this is the Ampere's law, which we will be going over also. You have the surface integral of B with respect to length is equal to mu sub ot times I. Okay, so here we have Faraday's law of induction, and it essentially relates magnetic flux to EMF. And yeah, so Faraday's law of induction is a basic law of electromagnetism, predicting how a magnetic field will interact with an electric circuit to produce an electromotive force. So this phenomenon is called an electromagnetic induction. It is the fundamental operating principle of transformers, inductors, and many types of electrical motors, generators, and solenoids.
How are you?
I'm hungry.
Well, I guess it's snack time. Let's see what food there is around here.
We have oranges and cereal. This looks good.
On Super Nanny, we like to provide nutritional snacks for our kids. Today's special snack is a speed stick popsicle. Loads of new scientific research has concluded that it is one of the best foods for high-performing persons. The ingredients include propylene glycol, water, sodium stearate, fragrance, sodium chloride, stearyl alcohol, bananas, cereals, and to top it all off, FD&C Blue number 1. The odd mixture of chemicals causes a chain reaction in the body, causing the recipient to go into a 15-minute coughing fit followed by a coma. Sometimes the coma and the coughing fit can be switched, and sometimes the person just doesn't wake back up. The coughing fit causes multiple abdominal fluctuations, increasing abdominal strength and mental endurance tenfold.
Alright, we have Speed Stick and Speed Stick Plus. Which one do you want?
Green? How do I eat it?
First, take off the cap. Spin the spinny thing at the bottle. And just take a bite. Okay.
So before I taught you Gauss's law, which can be used to calculate the electric field due to a configuration of electric charges. And Gauss's law says that the electric flux through a closed Gaussian surface, which is actually the integral of E dot dA over the area of the surface, is equal to a constant, 1 over epsilon, times the total electric charge enclosed by the surface. So there's an analogous law for calculating the magnetic field due to a configuration of electric currents. This law says that the integral of B dot ds around a closed loop called an Amperian loop is equal to the constant mu sub ot times the total current that passes through the loop. So yeah, and then so the equation on the sheet is known as Ampere's law, and we'll use it to find the magnetic field at points on an Amperian loop surrounding the source current. The circle on the integral sign in Ampere's law emphasizes that the integral must always be taken around a closed path. So,
for this
now you
problem,
try.
there's a rectangular loop next to a long straight wire. Here's the wire, here's the loop. And the wire has a current I, and the current inside of the wire is I sub m sine of W times T. And so it says that the wire and the loop are in the same page, plane of the page and are fixed in space, so we don't have to worry about any strange angles. Part A says using Ampere's law shows that the magnetic field intensity at a distance r from the wire is B is equal to mu sub I divided by 2 pi r, with mu sub being the permeability of free space. So the first thing is using Ampere's law. And so Ampere's law is just simply the surface integral of B times dl, which is equal to mu sub I, and then all we have to do is figure out what the area is going to be a distance r away. Since it's just going to be in a circular distance away, then it'll be b times 2 pi r is equal to mu sub I, and then we just simply divide this over, so divide both sides by 2 pi r. This one cancels out, 2 pi r, and then we're left with b is equal to mu sub I times, or divided by 2 pi r. And so that's the first one, and it's really simple. The second one says to find the magnetic flux through the loop at time t. So magnetic flux is equal to the surface integral of B with respect to the area. And so since this is an area that we have to find it with respect to, area of this like rectangle is going to be equal to the length times the radius or the distance away. And so when we take the derivative of A, the derivative of A is going to be equal to L with respect to R. And so we replace the dA in here with LdR. So that comes out to the surface integral of M is equal to the surface integral of B times LdR. Now, B in this instance is just, the magnetic field in this instance is just going to be mu sub I over 2 pi r, since we found that up here for any distance r away. So now we can go ahead and plug that into here as well. So we have the magnetic flux is equal to the surface integral of mu sub I over 2 pi r times L times dr. Now, if we look back up here, we realize that inside of the loop, the only possible values for r are going to be a, or it's going to be in the range of a to b, or a to a plus b. So with that in mind, we can just go ahead and set up the integral that we're going to be using, and that's going to be over here. The integral, or the magnetic flux, is equal to the surface integral from a to a plus b, because it's a down here to a plus b up here. And then inside it'll be mu sub I divided by 2 pi r times L dr. So now we can simplify this. It's mu sub or the magnetic flux is equal to mu sub I times L, because we're just pulling these out since they're constants inside of here, divided by 2 pi r, and then times the integral of this. And so since this is just leftover, or since leftover is just going to be a to a plus b, it'll just be the ln of a plus b divided by a. And so that one's not too bad. So the next question, the second C, this is probably supposed to be B, but we'll see. Says the current I in the long wire is in the direction shown above from T equals 0 to T equals pi divided by W. The direction shown above is to the right. It says indicate on the diagram above the direction of the resulting current that is induced in the loop at time t equals pi over W. So at time pi over W, the current is going to be equal to I sub m sine of W times time. That's right here. And time in this case is pi over W. So these are going to cancel out. So just a sine of pi. Sine of pi is -1. So it's just going to be so it'll just be I sub m equal to sine pi. And then we know that at this point it's just going to be coming out of the page. So we just go ahead and draw on here that distance r away at t equals pi over W. That's going to be going around, and so we know that now it's coming out of the page. So first, we know it's going into the page because the right-hand rule going this way, but then we have to reverse it, so it's going the opposite way. So then we have to do a resistance to it. So as we're to resist this, we have to add this so that it's going into the page or coming out of the page. And then using the right hand rule, if it's coming out of the page, then it'll be going around like this. So it'll be, since this is a rectangle, like coming around here. And so we can go ahead and draw that up here. And it's just going counterclockwise. So I can just write that here. All right, and so part 2 of this question says determine the EMF that is induced in the loop at time t equals pi over W. So the equation for the EMF is equal to the negative derivative of magnetic flux over the derivative of time. And so if we remember from up here, we're going to have to plug this in to here to figure out what the EMF is. So it'll be the negative derivative of this from up here. So that's going to be the mu sub I divided by 2 pi r ln of a plus b divided by a all over the derivative of time. And so now what we have to do is we have to go ahead and add in the or we have to put the I in since it's taking respect to time. So that'll come out to the derivative of mu sub ot L over 2 pi, it's ln of a plus b divided by a I, and then it's the one from up here, so it's I sub m sine wt all over the derivative of time. So now we just have to do some simplification, and so first we're going to simplify it. So it's negative mu sub naught L over 2 pi ln of a plus b divided by a I sub m. And then since we were taking the derivative, we have to use the chain rule. So it'll be w and then v squared times w t times w, and then I'll just be times a t and then t squared pi over w, and it'll be just w when pi is equal to -1. So finally, we come out and it's just simplified more. It's mu sub I sub m times L w over 2 pi, and then it's still the ln of a plus b over a, because we don't quite know where it's going to be inside of there. And so this is the magnetic, or this is the EMF that's induced when it's moving through. And so these are the 4 problems on here. There's not really much you can change about this. You might be able to say that it's going the other direction in the quiz, and so that he might do that to change it a little bit. He might also say that this is down here instead. So if it's going this way, then instead of coming or going into the page here and then coming out the page here, it would just be flipped. And if it's on this side, it would also just be flipped. If he does both of them, then it'll just be the same problem. So there's that, and I guess I passed the test. I'm gonna pass physics now.